This is Lecture 10G on the polar equations of conic sections. In this lecture, I will derive the polar equation form for the expressions for conic sections. I cannot promise this will not be painless, unfortunately. Okay, to develop these equations, what we do is take any conic section and place either the focus, if it's a parabola, or one of the foci, if it's an ellipse or a hyperbola, and place that at the origin of an xy coordinate system, and that's what we've done right here. Now there's different orientations. These could be a conic section in which the major axis is along the y axis or along the x-axis, but right now we're going to let it be located along the x-axis and put the directrix to the right of the conic section at x equal d. There'll be variations on this in a minute, but we'll just use this form to develop the expression for the polar coordinates. Okay. To do this, we make use of a relation from the previous lecture that was used to define the eccentricity E. E is equal to the distance from the focus F to any point on the conic section, FP, divided by the distance from that point to the directrix. This can be written in terms of r and theta, like this, only we're going to have to derive that. Okay, so let's start just finding the numerator. So what we're talking about here is a distance from the focus up to some point on the conic section. That green line right there. Well, in polar coordinates, that's just r. A line from the origin to some point is r, and that gives us the numerator. Okay, that should have been green color here, and I didn't have it. Alright, here I got it now. Okay, that's the r. Now the numerator's done. The denominator is going to take a little more work, and that's going to be the messy part. Here I've made a sketch that I'm going to fill in to use for the denominator in this expression. Right. So I need the distance from P to D. So from point P, which is this point right here, to the directrix D is, I'm writing as this. Right. I know that from my construction in the previous page, x equals d at the directrix. So this distance from the y-axis over to the directrix is the distance d. Alright, so this distance from point to directrix equals d minus this little section here, which for want of a better letter I'm just going to call g. I have r's and d's all over the place, so I'm just going to call that g. The question is, what is g? If you look here at, alright, going straight down, dropping the perpendicular down to the y-axis, and let's call this angle here theta, then g is equal to r, which is this radius here, times the cosine of theta, by definition of cosine. So now we can say that the distance from the point to the directrix, this distance up here, equals d minus r cosine theta, and that is the denominator right here. And now we're done. So we have the distance from the point to the focus divided by the distance from the point to the directrix written in terms of the polar variables r and theta. All that equals the eccentricity E of the particular conic section. Can rearrange this equation solving for r, so we have r as a function of theta equals the eccentricity times the distance to the directrix divided by 1 plus the eccentricity times the cosine of the angle. And as angle changes, as theta changes, like say oops, I need a pen. Say theta is this angle here, and this equation will give me this value r out to the to the conic section. I mentioned before I started that derivation that the conic section could have its major axis either along the x-axis or along the y-axis. It could open to the right or to the left, in which case the directrix would be located differently. It could be located at x equal minus d, y equals d, or y equal to minus d. In that case, the expression for the polar equations for the conic section will change slightly. Right? Here it's sine if you're in the y, if the major axis is located along the y-axis, located vertically. So you can see some minor changes here, and you could go back and redevelop all these, but we've developed it once, and so that's good enough. And here's a summary. In this case, the conic section is, well, theta 0. Say theta 0 is equal to 0, then this conic section would be oriented with a major axis along the x-axis, or in the direction of the x-axis. Here it would be located with a vertical major axis. Right. Theta naught rotates the conic section from being aligned with the coordinate system to an angle theta naught with respect to the coordinate system. So I'm going to try to draw that for you. So what we have here is the coordinate system. We'll just put, here's our x and y axes. If theta naught, this term, if this term is 0, then for example you might have an ellipse like that. Okay. Say theta naught was 45 degrees. Ooh, I don't know if this software will do this. Well, I'll have to draw it by pen. Okay, let me put a red one. Okay. Say theta naught was 45 degrees, so this is going to be 45 degrees. Then this ellipse would be oriented so that its major axis is at 45 degrees with respect to the x-axis. And you would have this form of the polar equation with theta naught at 45. Well, actually you should use radians. Okay? So the theta naught just allows you to turn that conic section off of the major axis.